Okay, in this video I want to talk about two theorems, the extreme value theorem and the intermediate value theorem. What they guarantee is actually pretty simple to understand. It turns out that it's difficult to prove. We're not going to bother with proving it because that gets into some advanced properties of the real number line. We're just going to introduce them to you, the results, and then so file them in the back of your head, and we'll use them on the AP exam, and then later on if you take more calculus maybe you want to prove it someday. I actually proved it and I was proud of myself, and it was pretty cool, but it took a while to get to that point. Okay, so let me motivate the extreme value theorem by showing you that not every situation do you have a biggest and smallest value. Okay, let me show you a question you will not be able to answer. What is the biggest value of 2x for x is less than 1? Okay, so you plug in all the values you like. X equals -5, x equals 0, x equals 1/2, x equals 3/4. Tell me which x value is going to give me the absolute biggest 2x value, okay, so that there's no other x value that will give me a biggest value. Okay, you're not going to be able to. So can you see that not every situation has a biggest value? Okay, again, here's another one. What is the smallest value of what's the smallest value of minus 3x for x is bigger than 2? Okay, so once again, plug in x equals 5, x equals 3, x equals 2.1, and you'll get a couple of values for minus 3x. Okay, can you tell me which x value will give you the absolute smallest out of all the infinite number of x values that are bigger than 2? Okay, once again, you won't be able to. One of the reasons, if you're wondering why, is because you can always get closer and closer to, in this last one, you can always get closer and closer to 2. There's no number right next to 2 on the number line. There's always space to squeeze in a few more. Okay. However, there are cases where you can be guaranteed that you have a biggest and a smallest value. Okay. That is what the extreme value theorem gives us. Okay, so watch this. Let me put that stuff aside, and it's going to use some terms we've learned in calculus. Okay, if a function is continuous, if a function is continuous, it is guaranteed to have a biggest and smallest value on any closed interval. Okay? So you have a closed interval, and if the function is continuous, thumbs up. You have a biggest and smallest value. All right, let me give you some examples where the extreme value theorem applies, and then let me give you some situations where it doesn't apply. Okay, so this, let me label what I just put here, the extreme value theorem. Okay, so here's a simple situation where it applies. So suppose that I wanted to find the biggest and smallest value of x squared for the interval 1, 2. Actually, let me make it minus 1, 2. All right, and so we'll make a sketch of the parabola. And we will label -1 and 2. and then we will see where the function is defined. We'll see where the biggest and smallest values are. So we need the biggest and smallest values between these yellow lines. Okay, now it should be obvious that the biggest value occurs at x equal to 2 at that green dot, and the smallest value occurs at x equal to 0 at that green dot. Okay, notice that the max occurred at the end point. That's perfectly fine. And the minimum occurred at an interior point. That's fine too. You can have one or both of those situations. All right. Now, suppose that instead of having that closed interval, suppose I changed it to, I want you to find the maximum value on this interval that's open on the right side. So it doesn't include 2. All right. Can you see that if the interval is open, it does not include one of the endpoints, you're going to have the same problem as you did with the black questions at the bottom of the whiteboard you couldn't answer. So you're going to keep getting closer and closer to 2, and you're never going to quite get to a maximum. Okay, so that's why it has to be a closed interval. All right, to satisfy the extreme value theorem. Let me give you another example. I'm going to give you now an example where you have a closed interval and you still don't have a max and a min. Okay, let's focus maybe on -1, 1 closed interval, and this time let's plot 1 over x squared. Okay, so now, between -1 and 1, looking at my plot, we're going to have to get the max and min on this between these yellow lines. And clearly, the smallest value within the interval, we actually have 2 minima that are the same, x equals 1 and x equal to -1. So we have those. Now, what about the biggest value? Okay, as you get closer and closer to x equals 0, to the origin, the function gets bigger and bigger, right? However, there's no biggest value, and we can't just plug in 0 because that's not in the domain. So here's another example where you have no biggest value. Okay, now why did this one fail the extreme value theorem? Because it's not continuous. It has to be continuous for every point in the interval. And this one fails at the single point with x equal to 0. All right, that's the extreme value theorem. Now let me talk about the intermediate value theorem. Okay, watch this. Suppose that there was a classroom, and suppose that there was somebody that was 14 years old, and suppose there was a couple people that were 16 years old and 13 years old. Okay, so what did I say? 13, 14, and 16? Okay, let me ask you a question. Is it guaranteed that you're going to have somebody... So wait, let me write these down. 13, 14, and 16. These are the ages. Okay. Is it guaranteed that you're going to have a 15-year-old? Okay, and the answer is no. There's no reason why you have to fill in all the gaps from the biggest to the smallest, right? Now, you might say that there's no reason you have to have every intermediate value between 13 and 16. Okay? Now, in some situations, you are guaranteed to have all the intermediate values between the biggest and smallest. Okay? Surprise, surprise, that's what the intermediate value theorem gives you. Okay? So let's talk about that, and we'll do some examples to flesh it out. So, intermediate value theorem. This says that if a function is continuous on a closed interval, it takes on all intermediate values between the smallest and biggest ones. Okay, now that's one way to say it. Let me say it a little bit more proper. Okay, or I don't know, maybe that one was clear, but let me just do it another way. Maybe some people have their tastes prefer this second version. You pick which one you want to memorize. If f of x is continuous on AB, then for all there exists an x value. Okay, if f is continuous on AB, then for all. Okay, so in other words, if you want an f value in between f of A and f of B, you can always find an x value that gives you it. Okay, I think I better quickly do an example to flesh this out. Okay, so let's start with a parabola, and let's draw that. Okay, and then let's say that we want to focus on 1 and 2, and yes, this is a continuous function, so we're good there. Okay, and so we're focusing on the interval, the piece between these yellow lines. Okay, and so let's figure out the function values at the endpoints. F of 1 is 1, f of 2 is 4. Okay, now pick any values between 1 and 4. You can pick 2, you can pick pi, you can pick 1.3. Okay, no matter what you pick between 1 and 4, I can find a x value that's going to give, that if I plug it into the function, it's going to give me what you want, what you ask for. Okay? For example, for 2, that's equal to f of root 2. For pi, that's equal to f of root pi. For 1.3, that's equal to f of the square root of 1.3. You see how I can always supply an x value to give you whatever you ask for? Okay? For 3, that's equal to f of root 3. Okay? And that's going to work for every single value in between 1 and 4. If it's continuous, and if you're dealing with a closed interval. Okay? Now, why would a function not satisfy the intermediate value theorem? Well, okay, imagine if a function had holes. Okay, or imagine if it skipped, like it was discontinuous. Remember how discontinuous means you have to lift your pencil to draw it? Well, if you're lifting your pencil because there's breaks, you can see that it's going to maybe miss a few y values. Okay, that's why discontinuity doesn't satisfy the intermediate value theorem. All right, now let me close by giving you an interesting use for the intermediate value theorem. Okay, you may be aware that your calculator can solve some, at least some of them can. You can give it any, well, not any ridiculous value, but you can give it some insane equation. Okay? And you can, some calculators, you can plug that in and say, give me an approximate solution, and it'll give you a decimal, and lo and behold, it can solve the dumb thing. Okay? Well, holy moly, how did anybody ever write software that could solve the most insane equations? Not only that, but it does it quickly. Okay? Now, would you be surprised if I told you that it's actually pretty trivial to solve insane equations like this? Okay. Furthermore, would you be surprised if I told you that it relies on the intermediate value theorem? Okay. Watch this. Here's the way we're going to solve it. And after I explain it to you, you're going to say, now it doesn't seem quite as impressive anymore. All right, let's do this. Let me first subtract 4 from both sides. Okay, and let me also give it a name. Let's call it C of x for a complicated function. C stands for complicated. All right, so in order to solve this puzzle, your calculator has to answer this question. For what value of x is C of x equal to 0, right? Okay. Now, suppose that your calculator plugged a couple of random x values, like maybe it plugged in C of 1, and let's say it gives you something that's positive. Okay? Now, also, suppose that the calculator plugged in C, and this equation is just an example. I'm not saying that if I plug in 1, this one's going to be positive. But suppose I plugged in like -2 and that gave a negative value. Okay? Now, let's make a plot. What does this mean? So we don't know what the C of x looks like. Or you could plot it, but and then you'd have an idea. But let's say, so at 1, it's equal to some positive, it's somewhere above the x-axis. At -2, it's equal to some place below the x-axis because it's negative. Okay? Now, if it was continuous between those numbers, okay, it doesn't have to be continuous everywhere, but if it's continuous at least between these endpoints, that means what? That means that I have to draw it without lifting my pencil. Can you see that there's no way that I'm going to draw a line from one green dot to the other without crossing the x-axis? Okay, there's just no way to do it. You're going to have to cross the x-axis because you're not allowed to lift your pencil. Okay, that's another way to see that the intermediate value theorem, another way to think about why it's true, because you have to cover all the points as you connect dots and not lift your pencil. Okay, now why is this significant? Well, we asked ourselves that we wanted to solve a function that equals 0. It's positive on one side, negative on the other side. Can you see that it's guaranteed that 0 is in between every positive and negative number? So can you see that the intermediate value theorem is going to guarantee that there's an x value that satisfies it somewhere? Okay, so this is what your calculator does. It plugs in a bunch of values for a function that's equal to 0. If it can get a plus or a minus, any positive or minus value, now it's in business. Now it focuses on the x values in between, okay, and then it gets closer and closer to a decimal that satisfies the equation, to the desired accuracy that you want. Okay, now what if the function was not continuous? Well, then your calculator is not going to be able to use the intermediate value theorem, is it? Then it's going to have to use some other way, or it's going to have to say, sorry, this one is too hard. I didn't say I could solve everything. All right? So that's a very nice application that's actually useful in the real world of the intermediate